Okay guys, I want to show you a real quick circuit analysis. Unfortunately, the program I'm using is a version of FET that is not HTML5, so it's a Java version, and Java has been now unsupported by Chrome and a bunch of other browsers. So if you can do this, it'd be great, but if you can't, I understand. So the lab packet I gave out has 3 problems that is meant to be a lab. It's meant for you to go and work with a partner and sit down on FET and build the circuit and then predict and figure out what's going on. So I've attached the lab to Google Classroom today. You take a look at it and follow along. What I did is, because my computer actually does run Java, it's a miracle, and it actually works, I built the circuit using this version of the program. And it's listed in the lab, but again, it's the Circuit Construction Kit AC/DC. Again, it's not HTML5, so you require Java to do this. What I want to do is I want to show you the circuit and see if it makes sense. And I've built all the parts. If you look in the packet on problem 1, I've built the circuit. It has a 9-volt battery. I've set these. You can right-click and change the voltage and set it to 9 volts. I can also check my voltmeter. So if I go to the top of the battery and the bottom of the battery, I can get a voltage reading on the multimeter of 9 volts. So I know it's a 9-volt battery. I've also put an ammeter in line. I've put a switch in line. I've put a capacitor, and the capacitor is 0.2 farad. Likewise, I right-clicked and changed the capacitance and set that to 0.2. And down here we have a resistor to burn off the charge on the capacitor, and likewise, the resistor has been set to 50 ohms, I believe. So I've set that to 50, that's done. So this circuit that you have here is the exact same circuit that is in your packet, problem 1. So the way it's written is you pause the video, you close the switch, and because everything's paused, nothing's happening, even though it's ready to go. So what I want to do is I want to hook up the voltmeter. Now the voltmeter, I've already checked it and make sure that's 9 volts. So what I want to do is I'm going to hook the voltmeter across the capacitor. I'm also going to put a clock in here. If I can find it. There's a stopwatch in here somewhere. I have my long glasses on there. And the stopwatch theoretically is going to run when I play the video. So when I run, it's going to actually give me the time. Now the reason why the time is important, if you look at the top, it's beeping. If you look at the top of the lab, we didn't actually do this lab, but I showed you this lab. The RC is called the time constant. So if you take the product, if you take the resistance and you take the capacitance of the circuit, that gives you a time constant. If you multiply that time constant, the RC product, by 5, that's 5 time constant intervals. And what that means is that the capacitor is done doing what it's going to do. It's 99.3% of the way through what it's going to do. In other words, it's almost totally at equilibrium or steady state or whatever you want to call it. It's a long time. And so for this circuit, because we have a 50 ohm resistor and a 0.2 farad capacitor, our RC is going to be 10. Therefore, if I run this for 50 seconds, the circuit will be done in the 50 seconds. Now, one thing to note is the clock on the stopwatch is not the same as a real clock. So the 50 cents they have in the 50 seconds in the simulation is not 50 seconds in real time. It's a little slower. So it's probably going to be 100 seconds in real time. But it's calibrated to the circuit, so it's actually correct for the circuit. So we'll let it run until it says 50, and you'll see the pattern here. Now, what I want to do is I want to do 2 things. I'm going to hook up my voltmeter across the capacitor, first of all, and I'll check it across the resistor as well. What I'm going to do is I'm going to do immediately after closing the switch. So what's going to happen is I'm going to run this thing and then stop it. I'm going to run it for as if I close the switch for a trillionth of a second. I'm going to run the simulation with the switch closed, and then I'm going to stop the simulation and see what our meter readings are, and that will be immediately after closing. And then I'm going to run it for 50 seconds, which will produce steady state. So the 2 columns on your lab immediately after closing the switch is analogous to me running a program for trillionth of a second, and then after 5 RC steady state will be when this thing reads 50. So I'm literally going to click and click to run it and shut it off. So ready, set, close the switch, close, open. Now, I probably let that go a little bit too long because it's really click. But what's happened here is that in the time that I've closed this switch, the capacitor started to charge. You can see there's a little bit of charge built up. There's a little bit of voltage. Now remember, this is a 9-volt battery. This thing is less than half a volt. So in that time interval, it hasn't had enough time to really put any charge on the capacitor. And the amps, the current in the circuit is relatively low. It's 0.17. Okay, it's 0.17 amps. Okay, if I check the battery, of course, it still should be 9 volts. And if this is 9 volts and this is less than a volt, the rest of it better be at the resistor. Because remember, the Kirchhoff's law says the battery's going to drive the voltage up, the component's going to drive the voltage down. So there better be a big drop, almost 9 volts, a little under 9 volts here. And sure enough, when I do it, it's 8.64. So again, this is going to be a little less than 0.4. And this will be the rest. So the sum of the gain battery equals the drop plus the drop. And again, I probably let this run a little bit too long because it really should be almost 0 here. This current should be maximum, if you remember how the charging and discharging curves look. Now, what I'm going to do now is I'm just going to hook this up across the capacitor, and I'm just going to let this thing run. I'm going to turn on this thing and wait for the clock to be up to 50. Let me run that, and that clock should be running, so let's start it. It's a little bit late, but again, that clock doesn't run at the regular time. It's 1, 2, 3, 4. The clock's a little slow, but you can see what's happening. If you look at the clock here, this thing's charging like crazy. It's driving up to 9 volts, but you'll notice when it gets closer to 9, it's going to slow down. It's like filling the gas tank. 7.5, 7.6, 7.7, 7.8, 7.9, 8.0, 8.1. It's slowing down. So as we get closer and closer, that curve is flattening out. And it's going to, you'll see it's now it's going 8.4, 8.5, 8.6, 8.7. So it's really slowing down. And that's what I mean by after that 5 RC, after, again, the RC here is 10. So after 50 seconds, it's pretty much done doing what it's going to do. And you'll see when it gets up to 50 seconds on the clock, this will be pretty close to 9 volts. I'll stop it, even though I didn't start it exactly the right time. You get the idea. So let's run a little bit longer. Now, it's too bad we couldn't do this in real life because it's kind of cool to actually do this lab the real way versus watching me do it. So there, yeah, that's not bad. 50.01. Now, if you look at this, we're at 8.9858. And of course, again, the battery is going to be 9. So where's the rest of that voltage? The rest of the voltage better be here. There's a tiny little fraction. Hopefully, if I hook up my thing correctly. There it is. My beeper's going off. Hold on. I don't know what that's for. Oh yeah, it's for roasting the oven. Okay, so so that simulation is the first circuit. So if you filled in the columns, you can have your data. You should see that. Oh, by the way, notice that the current is no longer flowing. The current's flowing as we're charging the capacitor. But once the capacitor is done charging, or almost done charging, the current dropped off almost to 0. And again, we'll see this if we do some other simulations on this. So I was just trying to show you the basic setup of how that works. Hopefully you're able to go back and do the rest of them, but we'll see.